All right, so this is our last video on energy ideas, and it's a little bit more complicated because it pulls together ideas for momentum and energy, and it's the second kind of collision. Before we had inelastic collisions. That was when objects stick together. Those are easy because you just use momentum conservation to solve for them. For elastic collisions, the objects, and we're going to talk about perfectly elastic collisions, there's no stickiness. The objects come together, bounce off each other, and there's no stickiness. What that means, when I say stickiness, what I really mean is there's no binding energy. There's no energy lost in gluing them together. So there's no appreciable potential energy. There's nothing like that. So the only forms of energy at play are going to be kinetic energy. That's it. So we're going to have two objects. They're going to start with their own kinetic energies, and they're going to finish with their own kinetic energies. They bounce off each other. So that's simple. So for inelastic collisions, because the objects stick together, there's only one final velocity. Whereas when you have elastic collisions, there are two final velocities. That means you need an extra equation to solve for this extra final velocity, and that's why you have to use both momentum and energy conservation. Momentum conservation always works in all collision kinds of problems. Energy conservation only works when things don't stick. Energy conservation only works for elastic collisions, not inelastic collisions. So let's push through this. Let's go. Well, we'll just do an example. I think rather than doing the arbitrary case. So in the book, you can see the formula worked out for arbitrary collisions. And it usually takes about 25 minutes of minus signs to prove it. So rather than do that, I'm just going to choose an example with fixed, with definite values, and we'll just see how it all works. And that's not so hard. If you want to see the full version, you can look in the book. I'll talk about what happens in the end. Experiment, like what actually happens when things bounce off each other, but I won't write down the actual formula. Okay, so let's imagine we have a cart and a cart, and I'm going to label this one 1 and this one 2, and I'm going to say M1 equals 1 kilogram, and I'm going to say that M2 equals 1 kilogram. This will be a simple case. Other situations, the final results might vary a little bit. And I'm going to say that the initial velocity for cart 2, so V2 initial equals 0 meters per second. And I'm going to say that V1 initial equals 1 meter per second. Now, we have two objects. We're going to have initial and final velocity, so we have to be very careful with our subscripts. So I'm giving you the initial information for cart 1 and cart 2. Excuse me, sorry. We're going to use momentum and energy conservation to solve for their final velocities. Since momentum is a linear sort of relationship, whereas kinetic energy is quadratic, I'm going to start with the linear stuff and go as far as I can with that, and then eventually switch over to kinetic energy. So I know, okay, so I have to make my system. If I make my system be both carts together, the whole thing, then I know there's no outside force acting on the system, which means there's no impulse or work being done on the system. So if the impulse is 0, that means the change in momentum of the total system is 0. If the work is 0, that means that the kinetic energy on the total system is going to be conserved. So I have two equations which say that the change in momentum of cart 1 plus the change in momentum for cart 2 must be 0. That means the change in momentum for cart 1 equals minus the change in momentum for cart 2. Okay? So that tells me simply that mass 1 times velocity 1 final minus velocity 1 initial equals minus mass 2 times velocity 2 final minus velocity 2 initial. Let's clean some of these things up. Let's plug in some numbers here. The masses were the same, so they canceled. And I don't know the final velocity of cart 1, but I know the initial velocity was 1 meter per second. For cart 2, I don't know the final velocity, but I do know the initial velocity was 0. So that cleans things up a little bit. So I have two unknowns. Masses are gone. Two unknowns. Excuse me. And I have one equation. So now I need to use the energy equation. It works much the same way. There's no work being done, so that means the change in kinetic energy for cart 1 plus the change in kinetic energy for cart 2 equals 0, or the change in kinetic energy for cart 2 equals minus the change in kinetic energy for cart 1. Now let's plug in what we know. 1/2 the mass times velocity 2 final squared minus velocity 2 initial squared equals minus 1/2 the mass of cart 1 times velocity 1 final squared minus velocity 1 initial squared. Phew. Wow. I know that the initial velocity for cart 2 is 0. I know the masses are the same. And I can write down the equations that I have. So I have two equations here. My equations are V1 final. I can rearrange that. V1 final plus V2 final equals 1 meter per second. I'm just rearranging the momentum equation. And from the energy equation, I can cancel the 2's as well. I'm going to move this first term over. And that's going to say V1 final squared plus V2 final squared equals V1 initial squared, which is just 1. Should we use that? This is just 1. And that would be meters squared per second squared. Very good. All right, so I've just taken my momentum and kinetic energy equations, rearrange them a little bit, cancel things that should cancel, and I get that equation. Well, what can I say about that? Well, that's kind of a tricky one. If you're a little bit clever, though, you can make it work out nicely for you. Take the top equation and square both sides. So what we would learn, if we take the top equation and square both sides, is that V1 final squared plus V2 final squared plus 2 V1 final, V2 final equals 1. But on the other hand, V1 final squared plus V2 final squared equals 1. But the only way that can happen is if V1 final and V2 final equals 0. So if you subtract these two, you learn that 2 V1 final, V2 final equals 0. So either the final velocity of cart 1 is 0, or the final velocity of cart 2 is 0. Well, cart 1 hits cart 2, right? It's moving to the right. So I know the final velocity of 2 can't be 0. It's going to bump forward. So it must be that V1 final is 0. And so what you have here is a situation where cart 1 moves forward, collides with cart 2, and transfers all of its momentum over to cart 2 and stops. So what we find is final velocity 2 final equals 0. So here's what happens, and it depends upon the masses of things. If you have a smaller mass thing, which runs into a stationary large mass thing, the large mass thing will move forward, but the smaller object will recoil and bounce back. So it's kind of like, if you ever watch a little kid play with the big kids, he or she can run into the big kids, but then they inevitably fall backwards. On the other hand, if the cart which starts out moving is bigger than the target cart, it just plows right on through. The target cart bumps forward, and the more massive cart keeps going forward. It's kind of like if you throw some marbles in front of a car or something. I don't know. If the car hits the marbles are going to fly forward, and the car is going to keep moving forward, so you're going to notice the difference. If the two objects have the exact same mass, then the momentum of the first cart or object is wholly transferred over to the target object, and the target object moves on forward with the same velocity as the initial cart had at the beginning. And that's how that goes. So there's a general formula, and you can see the minus sign switch depending upon masses of this and that. But and it's in the book. So if you want to do that, you can. I think the sapling examples are all explicit like this, where you just know the numbers and you just do the algebra. So, all right, that wraps up our discussion of energy and momentum and conservation laws as a whole. Next up, we're going to talk about rotational properties and torque, and that'll be our last topic of the semester. All right, talk to you guys later.